Okay, Doug Littrell again, in my living room again. Got the paper with the adhesive spray on it again, and I'm talking about nuclei again. I'm going to talk about a few more things today. This is video number 34 on July 17th, 2017. This configuration, these would be neutrons, would be that of oxygen. That's the spine of neutrons and oxygen. That's what I've come up with. You would have 4 protons wedged on both sides, like that. Those two here. That keeps them evenly spaced. Now the neutrons can get very close to one another in these configurations. They just can't touch. It's when they're very attracted to one another. The neutrons are very attracted to one another. But when they touch, then they jump apart because there's too much surface repel. The protons don't have that problem when they're up against either neutrons or other protons. So the protons are a milder particle. I want to show also the nitrogen frame. Yeah, now these are frames. There's a problem with carbon. Let me show the carbon frame next. With carbon, it's just like this, and there's nothing in the middle. It's like oxygen, but there's nothing in the middle. You have this. You have 4 on this side. Yeah. And then you got 2 over here. And if you get them spaced just evenly, you can put 4, 1 here, 1 here, 1 here, 1 here, and then have 4 more on the other side. And that would be carbon. It lacks that center one that oxygen has. And from doing this in the past, I've decided that there's a problem with building out on carbon, to have that the underlying frame of a nucleus in the larger nuclei. Now that could be wrong, but what I'm doing is right now I'm alternating. When I do these larger nuclei, I build one on the nitrogen frame, then I build one on the oxygen frame, and just alternating like that. Seems to be working out. Let's do the nitrogen. I'm mentioning that, and I haven't even shown it. Now, the nitrogen frame is basically the beryllium frame, and that's what you have. And in this case, you have 3 protons on each side, I'm only holding 2, but there would be another one here. And they would hold the neutrons away, keep them from clapping, and they would wedge. And so that would be 9. So that's the nitrogen frame. And nitrogen, you just have more. You have not only those, but then you have some on each side, some protons on each side, 3 of those. So now you've got 9, 10, 11, 12, and then you've got, when you have this threesome of protons in the front and on the back, you can place another proton on top. Now the reason it doesn't have a neutron in that spot is because it's a gas. You get a powerful neutron that far out, now that changes things up quite a bit, and now it's more attractive, and now it's going to be more apt to behave like a gas, or let's say a solid or liquid instead of a gas. But anyway, there's a lot of factors that go into why these would make gases or solids or liquids. You've got radio shell distance from the nucleus. You've got that particular nucleus of those can hold. You've got also how far extended out its neutrons are on the surface. If they're covered over by protons, that makes it a milder, attractive nucleus when you come down to talking about, you know, this nucleus is attracted to another. Now, these diatomic gas molecules, they're attracted enough that they make diatomic molecule. Two of them attach, and that's a gas. Well, in oxygen, three of them can attach. In my system, oxygen is a pretty flat nucleus, and so its shell, all radio shells, outer shells, and shells, they're pretty much perfectly spherical. In oxygen, it would not be that way, and so oxygen can make O3, it can make O2. So all of that is affected by how these are configured. I want to mention some things about, let's say, gravity waves, for example. Now, a wave, all a wave is an outward spreading emission of usually photons. It can be radio particles of a certain type or a certain combination, but it could be photons, and you have a certain concentration in one wave and then a low concentration behind it. That's the dip in concentration between two waves, as they're arriving in certain intervals, and that's what you have with a wave, is concentration, lack of concentration, concentration, lack of concentration, and they're arriving. Okay, that's all a wave is. Now we've got in scientific explanations that are used today, right now, anyway. A wave is meant to explain something that's, so we say it's a wave, and then we don't have to talk about it anymore because we can't understand it. You know, that's a system where everything doesn't have to have mass like mine does. But the absurdity of a wave, of gravity waves, let's say. Okay, what holds let's say, a neutron or a proton, what's holding that unit together, it's photons. What it can, you know, some people might try to say these contain something else, not positrons like I do. There's not there's not a center unit in each one surrounded by 14 positrons with electrons jammed in a few of the valleys too, and then some more photons as well, and some radio particles also. They will say that these have something else inside of them. Okay, well, they can say that. I can say this. We'll see which one holds up better. But what's holding those together is attraction. What's inside of the particles inside of these are attracted, okay, and they attach. And it's the analog of gravity. That's analogous to gravity. Are you going to say that that these particles in a neutron or a proton are sending waves to one another? That is so absurd. That everything's sending waves around? No, it's just continual attraction. It's continual attraction. Let's say attraction between two bodies where there's orbiting, okay, in the cosmos, a star and a planet, okay? They're reciprocating attraction, gravity, okay? The gravity is not turning off and on at intervals like a wave. It's constant. It is massless. Now we have something they're treating this concept as a wave when they talk about gravity waves. Like now it's some substance. It's like it's arriving at interval. No, all of that they're sensing is the different. you're talking about the 100th or 1,000th the diameter of a proton. They can sense movements, and then they have these mirrors set up 2.5 miles apart. And you don't think that the variation in seismic waves is going to vary by 1,000th of the width of a proton? That's all BS. That's BS. Okay. If you believe in composite particles at all, and they have to attract and attach to be anything, and then to say that their attachment or their attraction that makes them attach is sending out waves to one another, that's ridiculous. Okay? Let's talk about temperature a little bit. We're told by some scientific explanations today that there are such a thing as millions of degrees. Well, guess what? There's no such thing as millions of degrees. You want to know why? I'll tell you exactly why. And this is not counterintuitive, and you can understand it with an average person can understand this because it's like the world we live in every day. Okay? When you have radio shows, now I've seen this with my own naked eyes while looking at direct sunlight through cotton fabric. In 2011, I did this 12 times. I looked at the sun. There are some larger atoms that are attached to cotton fibers, and they lens, that is, they magnify because of the direct sunlight, and you can see them. Okay, there were radio shells, what I interpret as radio shells surrounding each of these larger atom nuclei. Out from there were either 3 shells or 4 shells. 4 in the larger ones, 3 in the smaller one. That's how I've designed my atom model, based on what I saw. Also this, on the warmer days, it didn't have to be a lot warmer, but on the warmer days, another shell, a black circle line, appeared just outside that gray shell, radio shell area, what I call a radio shell area, where the radio shells are layered and completely filled and spherical. What happened had to have happened on warmer days. There was enough incoming radiation particles and that were pelting the outer shell and the other shells as well, but mainly the outer one, that it vibrated so much, so violently, that it spawned, some of those came out farther, but they weren't lost by the nucleus, and then they were exposed to that and began to orbit. That's heat. See, with heat, you need 2 things. You need friction, which is caused by particles arriving and hitting. That's friction. That's heat. If you have it's ongoing, that's heat. Okay? There's no such thing as heat without mass. All right? There is no such thing as heat without mass. You have to have friction to have heat. Okay. Now, if there's no atoms present, it's over. At the moment it's off, it's over. There's no heat the next moment. If there are atoms there, the only way heat can be prolonged, carried forward in time, is by momentum of an orbiting shell. If you have a shell that's not filled and it can orbit, then it gains momentum because it's orbiting, and then you can have prolonged heat, and it's also striking things coming by, and that's friction and that's heat. Okay? That's heat. There is no such thing as there's a limit to that. There's a limit to how fast those orbits can go. But when you have momentum and orbiting, and those things can collide as well, now you have a reason for heat. You got a way to describe it, and it's only going to accelerate to a certain level. There's got to be some sort of limit to temperature as far as heat. I don't think there's anything that can approach millions of degrees. Okay, I think that's we're told that things fall through space at the same rate. I've already shown balls of different mass rolling down a track. That's false. I've shown objects of different mass fall through the resistance, equal resistance of water, and the heavier one always gets there first. People stand on their feet next to one another. Somebody weighing 250 pounds compared to somebody that weighs 100 pounds or 150 pounds. They press down on the floor. Those all correspond a different amount. Those all correspond. That's the natural world we live in. You don't disprove that by dropping a couple of rocks off of a tower. There's so many explanations in science right now that, you know, as far as doing applications you can't cheat, because you have to actually accomplish something. You can't cheat with applications. They're good at applications, but explanations, scientific explanations right now are some of the worst. I mean, as far as actually knowing what's going on and explaining it correctly, scientific explanations, so many of the scientific explanations are so bad right now, it's ridiculous. They're like religion. It's like a religion that's passed down like dogma. And people want status, and they get their degree, and so then they don't want to challenge it because they just want the status so they can make money, and that's it. And nobody cares about what's really going on or how it might change the world and might get rid of evil religions like radical Islam. We could get rid of radical Islam if we knew what was going on in science better and explain things by the natural world, and we realize there is no such thing as all these counterintuitive spiritual realm baloney, phony baloney junk that we don't need to believe in, that nobody needs to be afraid of or pay any attention to it. We can just get rid of that stuff. Everybody can realize that and get rid of it. That's how important it is, getting these explanations correct.